Welcome back to another calculus video. Today we're going to dive into a new unit and a new way to look at the slope of a curve. And we have a new word that we're going to start using to describe that slope of the curve, and that word is the derivative. And so now we're getting into typical calculus where we talk about limits first, and now we're getting into derivatives. And really, you have been finding derivatives all along. If you've been following along with this series and you followed our series on limits and you learned about the rate of change as it relates to a limit, every single time you were doing one of those, you were finding the derivative. So let's dive in and see what we have going on here. So we've defined the slope of a curve at some value a on the curve using this limit here, f of a plus h minus f of a all over h, and the limit of this quantity as h gets smaller and smaller. Remember, what you're doing is you're finding the slope between 2 points on the curve, and those points are just getting so close together, and h is the difference in the x values between the point you want to know about and the point that's getting closer. And so as that point approaches, the slope between those two imaginary, or the point and then this imaginary point that's getting closer and closer, the slope between those 2 points, the limit as h approaches 0, is the derivative at a. So we're going to call this the derivative from this point forward. And this is the definition of the derivative. So we can find a derivative at a specific spot, or we can find an expression that describes the derivative anywhere along the curve. So we want to understand what we are, what we're looking for and what the problem's asking us, because sometimes we want it at one location, in which case our answer will be a numerical value. Sometimes we want that equation that describes the derivative anywhere along the curve, so we can pick a location and it'll work no matter where we are. So let's talk a little bit about some of our notation. When we refer to the derivative, we use this notation f prime, and that's what this is right here, and this little, it's just a little apostrophe up there. F prime of x is the notation and the wording that we use when we describe the derivative. So to find the derivative, what we do to find the expression is, instead of having a plus h, we just use x plus h. And then we have a value that has two variables floating around. We've done this before. And this is how we find the derivative. So this will give us an expression or an equation, and that will allow us to find the derivative anywhere along the curve. Now, sometimes this limit will not exist. And remember, in order for a limit to exist, coming from the left and coming from the right, you have to have the same value for that limit. So there are times when we cannot take the derivative, and we're going to see some of that later on in this unit. But just a couple of words that I'm going to use throughout this video and throughout our lessons here. The derivative, that's a noun that describes either a numerical answer or an equation. When we can find the derivative, the process that we're using is called differentiation. So we differentiate to find a derivative. So differentiate is our verb, derivative is our noun. So there you go, English people. So let's go ahead and find an equation for f prime using that derivative definition. Now, there will come a point when you won't have to do all this work. There are some shortcuts along the way. So as we do this video, in the back of your mind, I want you to see if you can identify a pattern throughout all the work that we do, because later on you'll be able to apply that pattern. But for right now, in this video, we have to understand the limit. It does show up on the AP exam, and you are responsible to know it. So here we go. We're going to find the equation. So first of all, we need to find f of x plus h. We have f of x. It's in the problem. So f of x plus h is simply what I get when I plug in x plus h in for x. So I do that composition. I plug it in to my f of x equation. Now, here's the fun part. I have to multiply this guy out. So I'm going to have to write this out. And this is what's less fun about these problems. I'm going to have to write it out a couple of times here, and I'm going to have to multiply through. So I'm going to go ahead and do these two at a time. Remember, when we have multiple binomials, more than two, like here we have 3 binomials, you have to multiply them 2 at a time. So x squared plus 2xh plus h squared, and then x plus h. And then I'm going to use my distributive property. So I'm going to have, I'm going to go ahead and distribute the smaller one into the larger one. So I get x cubed plus 2x squared h plus xh squared. Now I'm going to distribute the h through, plus x squared h plus 2xh squared plus h cubed. So when I clean this up and combine some like terms, let's see, I'm going to have x cubed plus 3 x squared h plus 3xh squared plus h cubed. And some of you may know like a shortcut for expanding the cube of a binomial. If you know that, you can always apply that here and just jump straight to it. There is a pattern involved, and maybe you can pick that pattern out. I tend not to rely on remembering tricks and patterns and just remembering, you know, the process to get there. Because I always forget the tricks. Your math teacher forgets them, so I can always multiply it out though. So here we go. The limit as h approaches 0. Here we go. F of x plus h is this big long polynomial that we just found. And we're going to subtract from that x cubed. And this is all over h. And I'm going to go ahead and draw a little line so that my work stays separate, so I don't accidentally throw an extra x cubed in there. So now I'm going to cancel some things out and start simplifying. So the limit as h approaches 0, let's see, we have 3x squared h plus 3xh squared plus h cubed all over h. We're going to go ahead and factor out that h, you know, like you do. And then it cancels away nicely. And now when I substitute 0 in, the only thing left is simply 3x squared. And so what we would do here is we would write that definition of that derivative, or we do all this work, we get to the end, and we'd say f prime of x is 3x squared. So again, there's my derivative, and there's my original function. So the derivative of x cubed is 3x squared, and I can pick any location along my x cubed and plug a number in, and I can find the slope of the tangent or the slope of the curve. Remember, those are all the same things. So here now I have an equation. I can find the derivative anywhere, and I can write the equation of a tangent line for anywhere along my x cubed curve. So let's go ahead and do that. Let's write an equation of the line that's tangent to f of x at x equals 2. So I need a point at x equals 2. Now to find that point at x equals 2, I need to find it on the original curve. So I need to find the y value. Y is f of 2. So I'm going to plug it into the x cubed. So I have 2 cubed, that's 8. So my point is the point 2, 8. Now my slope is going to be the derivative at 2. Well, we have an equation, so I'm going to say find f prime of 2. So here we go, 3 times 2 squared. 2 squared is 4. My derivative is 12. So my equation is going to look like this. I'm going to use that y minus y1 equation. So y minus 8 equals my slope, x minus 2. So the slope is the derivative, and the point comes from the original function. So it's really important as we are kind of getting into doing some of these bigger problems. You're going to encounter situations from this point forward where you're going to have f of x and you're going to find f prime of x. There are going to be instances where you find f double prime. We're going to talk about that later on. There are derivatives of derivatives. And you're going to have multiple equations floating around in your problem. And so it's really, really important to label everything clearly. On your AP exam, if you circled 3x squared, you wouldn't get credit for it. You need to label it. You need to include that this is f prime of x. So clearly label every single equation. Make sure that you refer to every equation properly, that when you're talking about the derivative, you're writing f prime of x and all that good stuff. So it's easy to accidentally plug a number into the wrong equation. So go slow in the beginning, label everything. So let's talk a little bit more about some derivative notation. So when you look at the history of mathematics, calculus was, the concepts of calculus were being explored by mathematicians all across Europe. Isaac Newton has the most credit because he was actually historically the first to kind of come up with these ideas on a grand scale. Now, that doesn't mean there weren't other mathematicians exploring ideas of rates of change, but Isaac Newton was one of the first to nail it down. But he was not the first to publish. Gottfried Leibniz was actually the first to publish. And so there was actually a lot of tension back in the 1600s between Isaac Newton and Gottfried Leibniz, because they were fighting over who came first. And Isaac Newton wrote some pretty awful letters about and to Leibniz because he was so angry that Leibniz published first, and he said, "You stole my work." And it was lots of drama. But in any case, we have these two guys who at the same time were developing these ideas based on ideas that were coming forth from other mathematicians and other concepts that have already been talked about and discussed. You know, that's what math was. There were no textbooks. It was people getting together and discussing things, people writing letters to mathematical societies saying, hey, what do you think about this idea? Here's this theory, here's this theorem. I need help proving that it's true. Can you help me come up with a proof? And so this is what was happening. And there are still concepts today that people are discussing in these mathematical societies. So it's not just pick up a textbook and learn math. You think about, you know, one of the biggest concepts happening today is a question about, you know, what's the largest prime number and does one actually exist? So this is a concept that is being discussed now, here, today. What's the biggest prime number, if in fact there is one? So this is how math is. Math is not just come to class, open a book, and do some problems. Math is, let's discuss what we see happening with numbers. And so this is what was happening back in the 1600s. And so Isaac Newton had his way of expressing a derivative. And so this f prime, this was Isaac Newton's notation. And it's great and it's easy, and we're going to probably use this quite often because it is much more succinct and easy to use. Y prime is another way to express a derivative. So if we have something that's not in function notation, we can refer to the derivative as y prime. Leibniz used this notation here, dy dx is how we say that. It comes from the slope formula, and it's the idea that it's the difference in y divided by the difference in x. So the change in y over the change in x, this is a differential kind of ratio that we have. And so Leibniz used this to express that when he's finding this derivative, he's finding a rate of change. So Leibniz notation has a, it's necessary for some of the things that we're going to do later on in this unit. Some other ways to express the derivative, sometimes we might use this d dx and then put f of x later on. So for example, f prime, the one we just did, we would write it like this, d dx. That means take the derivative of this function and then find it. So that's what we did in example 1. Another notation that I don't use this one very often, it shows up df dx. That just means the derivative of the function, the rate of change of the function, and we say with respect to x. So think about the slope. You know, when you find in a distance over time problem, the rate of change, the slope of your line, represents your, you know, miles per hour or whatever the units are. So you're saying for every 1 unit increase in x, what happens to the y variable? So for every hour that passes, my distance covered increases by 60 miles per hour. Well, that's what this notation is saying. For every increase of 1 in my x variable, what is the expected change in my y variable? That's really what derivatives are helping us to find. So let's go ahead and make a connection here. If f of x is the slope of the curve as well as the slope of a tangent line, where on this graph would we find negative derivatives and where would we find positive derivatives? So are there other important spots that we would notice? So let's think about this. Remember, if we pick any point on the line and sketch a tangent curve, right, or a tangent line, there it is. So right there, that line, remember, positive slopes go up, negative slopes go down. So this is a positive slope. And if I pick another curve, another point on the curve right here, oh, that one also has a positive slope. But then if I go to the other side over here and I connect my tangent line right there, that line has a negative slope. And as a matter of fact, anywhere on the left side of this parabola, I would have a tangent line with a negative slope. So let's talk about what's happening in the graph. On the left side, where I have my negative slopes, my parabola is coming down, so it's actually decreasing. Where the function is decreasing, so decreasing on f of x, that's going to have a negative f prime. Where we were increasing on f, you're going to have a positive f prime. And that's something to kind of make a mental note of. That's an important thing to recognize. Now, my other question is, are there any other important points on this graph that you would notice? And what I want you to do is I want to draw your attention down here, and I'm going to use the rainbow pen because this is really important. We've actually kind of discussed this before. Right down here at the very bottom of my parabola, I have a horizontal tangent. Now, this parabola, we call this point the vertex, but what I want you to remember is that the vertex of a parabola is either a maximum or a minimum value on the function. So we have a horizontal tangent. Here it's a minimum. If my parabola had flipped over so that my vertex was a maximum, I would also have a horizontal tangent. So what I want you to remember is that at minimums and maximums, the derivative, f prime of x is always going to be 0. Now, I want to make a note that that's not the only criteria, because I can make a sketch of a graph where I have a derivative that's 0, but it's not a minimum. So for example, if I go over here and I make a sketch of a graph that looks like this, and I tell you that right here at this very center point, there is the tangent has a horizontal line, and the derivative is 0. But is this a maximum or a minimum? Clearly it's not. Now, what is the criteria for a max or a min? Not only does the derivative have to be 0, but we have to see something happening on either side. On the function, if it's a max, my graph has to go up to the max and then come down. So it has to turn around and come back. Same thing for a minimum. It has to go down and it has to turn around and come back. So not only do I need to see a derivative that's 0, but I need to see that increasing, decreasing change. In other words, I need to see my derivative change from either positive to negative or negative to positive. So I'm going to make a note of that, and if it's written in rainbow, you know it's super important. F prime changes sign. Now this is going to become more significant later on, but it's always important to introduce this concept so when we see it again, it's not hitting us for the first time. So when there's a minimum or a maximum, not only is my derivative 0, but on either side it's going to change sign from either being positive to negative if it's a max, or negative to positive if it's a minimum. So let's take a look now and see if we can take what we know and make a sketch for a derivative. If I give you the graph, can you tell me what this derivative would look like? So here's our first example, y equals x cubed. Now we know the derivative of this one already, but let's see if we can make a sketch of the graph. Now keep in mind, we found the derivative was 3x squared in example 1. Well, that's a parabola, so our graph should look like a parabola. So let's see if we can trace along it and see. Now, as I trace, I want to see that, well, I've got positive slopes here. In the middle, I seem to have some sort of, my slopes of my tangents kind of, let's see, they're positive, they're super steep, and then they get less steep, and then eventually it looks like they kind of flatten out and maybe have a slope of 0. Well, and then they stay positive, so it stays positive everywhere along here. So when I sketch this derivative, when I try to match the derivative, in the middle it should have a 0. So I'm going to go ahead and plot that at 0, 0, and we can see that right here. At 0, 0, I should have a 0 derivative. And then my derivatives start out nice and steep, so they're going to be super duper high. So remember, this is the graph of f prime of x. So over here to the right of 0, remember your x values are going to stay the same. So like, for example, when x is 1, if we go up here to when x is 1, let's see, there it is. When x is about 1, you can see that my graphs kind of have slopes like this. And as I get to 2, my graph is going to increase. My slope is increasing, increasing, increasing. So we start out low, so maybe we have, smaller slopes here. And then the slopes, so remember, the y on this is your slopes. Your slopes are going up. And then the same thing happens on the left-hand side. Even though it goes down below the y-axis, your slopes are still positive values. And they start out less steep, and they get more and more steep. So if we know that our derivative is supposed to be 3x squared, like we found in example 1, we should see a parabola. So when I make a sketch of this, my graph should kind of follow this basic pattern. So let's see what happens when we show it. Oh, there it is. And yep, the derivative, the graph is a parabola. So let's take a look at another example here. Ooh, now we have this one. It's an upside down parabola. So as we take a look and make a sketch and see what's going on here, remember we're graphing on the y, we graph the slopes. So again, so here's f prime. These are your slopes. Now on this graph, I have positive slopes on the left, and I have negative slopes on the right. So on the left-hand side, I should have positive values. On the right-hand side, I'm going to have negative values. So let's see, they start out very steep down here, and then I do pass a 0 point. So at 0, 0, I'm going to have a slope that's 0, because I have that maximum, and it flattens out. So the slope of the tangent at 0 is a flat horizontal line. On the left, I have positive. On the right, I have negative. So what happens is, let's say that I'm over here at, some big value, like, or over here at -5. The slope there is really steep. So I'm going to put a dot pretty high up here. It's a positive, steep line. And as I approach that 0, my lines get less and less steep. When it hits 0, all of a sudden my lines begin to have a negative slope. But the same pattern happens. Remember, the steepness means I'm going to get further from the x-axis. So the steeper my tangent line, the further from the x-axis. So this looks like it might be some sort of kind of straight linear function. Let's take a look and see what happens when I do this derivative. Oh, look, that's the pattern we saw. So you can see on the left-hand side here, I've got positive slopes, so my derivative values were all positive y's. Over here, my slopes are negative, so when I plot the x-coordinate and the slope, I should be in the negative territory. Let's just do one more here. Here I've got this, this is just a line, and you can see that the slope of the tangent, well, this is curious. The slope of the tangents, if this is a line, shouldn't they all be 3? Wouldn't the tangent line just be the line itself? So wouldn't you see derivatives that just kind of stay that slope? Maybe the derivative of this is 3, because the slope of this line is 3. Let's see. Would you look at that? This is the line y equals 3. So when you have a linear function that has a slope, remember the derivative describes the slope. If the slope is the same everywhere on the curve, then your derivative will be a horizontal line. It will be a constant. So that was kind of a fun little activity. So now, the last thing that we want to talk about here is what happens when we have data in the real world and we need to estimate based on real world data. So let's take a look at what we have going on here. We've got an object moving in a straight line, and a physics student measures the distance the object has traveled from its initial position at various time intervals. This is the data table of the graph in question. So let's take a look at this and kind of zoom in just a little and see what's happening with this data table. Okay, so now that we have a little better view here, let's understand the problem. So we have this object moving, and this physics student is measuring the distance at certain time intervals. And so here we have x is measured in seconds. So after 1 second, this object has gone 2.2 meters. So we're measuring in meters and seconds. So every slope that we find is going to represent meters per second. So what's happening here as we follow the curve, after 2 seconds, my object is now 12.3 meters away from where it started. So we can see and hopefully you can agree with me, that this object seems to be accelerating. It seems to be going faster. It does not have a constant rate of change. So it's faster from 1 to 2 than it was from 0 to 1, and so on and so forth. So it's following this curve of getting faster and faster and faster. And so what we want to do is we want to estimate the derivatives. We want to estimate the rate of change for this function. We want to see what would the derivative look like. And so as we look closer at this, we say, well, this is real world data. I don't have an equation to model this. And we could put it into a model, or we could come up with some equation. But really, truly, what you want to do is you want to use the data that you have to estimate the derivative. And we talked about this when we saw the rock dropping in the previous series. And we said, well, the instantaneous velocity, that's what we're really finding here. When we have distance and time, we're finding velocity or speed. When we find the instantaneous speed, that's the derivative. But now what we're going to do is we're going to find the average speed. We're going to find the average rate of change and use that as an estimate for the derivative. Because really, if we're connecting these 2 points with some horizontal line, you have to assume that this is some sort of continuous smooth curve and that nothing crazy happens. You have an object moving along at a smooth pace. So you can make the assumption that this would be a continuous function. And if we can connect any 2 points, well, that's going to be pretty darn close to estimating kind of where the derivatives fall. That would be the average of the derivatives along that curve. So what we do is we say, well, I'm going to estimate the derivative between the 2 points, at the midpoint. So when I sketch this curve and when I want to draw my little connections, the connections might look something like this. So, for example, these 2 points are nice and easy to see. Remember, the idea is that this curve would be some sort of smooth curve. And remember, all the tangent lines, they're pretty close to parallel to that pink, we call it a secant when it connects 2 points. So the tangent lines would be really close to being parallel with that secant. They're not going to be parallel, but they're going to be pretty close. But I also think that maybe it's quite possible that somewhere between the 2 points there would be a tangent that's parallel to the secant. I don't know. Maybe that's something we'll explore later on. So the idea is the slope of this will estimate the derivative. And so we're going to nail it down to one spot, and we're going to pick the midpoints for our x values. So like, for example, if this goes from 0 to 1, I'm going to pick 0.5 to estimate my midpoints. So I'm going to use the slopes. Those are my derivatives, and the midpoints are the x's. So when I find the slopes between the 2 lines, back to my table here, that's what we're going to do. So here's my data, and I'm going to find the slope between the first 2 points. So my first x would be 0.5, and then f prime, I'm going to go from 2.2 to 0 to 2.2, 0 to 1, and I'm going to find that slope. 2.2 minus 0 over 1 minus 0. Oh, it's just 2.2. So the estimate of the derivative between the first 2 points is 2.2. We would say that the average velocity over that time period is 2.2 meters per second, and that's the estimate of the derivative there. So that means the next x value is going to be between 1 and 2, so I'm going to pick the midpoint there, 1.5, and then I'm going to find the slope between those 2 points. So I'm going to do 12.3 minus 2.2 over 2 minus 1. And that gives me, let's see, that gives me my slope. So there we go. So you can see, and if we scroll on down, here's the completed table. Let's see. Oh, that's a different example. Let's see. If we were to plot these points and take a look at what the derivative looks like, it might look a little something like this. Okay, so as we can see, the purple dots here, that's my original function. And then as I found the slopes at each midpoint and plotted them, we can see that this graph seems to be kind of linear, this derivative. And so this is the rate of change, and these would be the speeds. So remember, the red graph and the purple graph would have two different y-axes. The purple graph, the y-axis is going to be the distance in meters. And then the red graph would be the derivative, which would be the rate of change, which would be the speed or the velocity. So this is how we can estimate derivatives using the real world data. And so remember, a derivative is a slope. And so if you don't have the actual value, then you use the slope between the two endpoints and kind of estimate the derivative. Because somewhere between those 2 points, you're going to find that derivative, assuming that your function is continuous. So let's take a look at one more. And for this one, I'm not going to go through the work of finding the slopes between the points. I just want to show you another example. And let's talk about this. If this was my object in motion, here, these green dots, let's talk about what we see here. We see this object, it starts off and it's 0, 0, so it's starting at the beginning, and it speeds up. Okay, so if this is velocity, that means it's going forward, and then from 1 to 2, it's going forward a little bit faster because the slope between those 2 points is steeper. So the steeper the increase, the faster it is. But then notice it comes down. So we have to understand what's happening there, because at some point, the distance from where it started is decreasing. So this leads me to believe that maybe this object is moving, and then all of a sudden somewhere it stops, and then it turns around and comes back. And the rate at which it comes back initially is a little steeper, so it's going to have that steeper, so it's going to go out and then back, and then it continues backwards. So we actually see that the rate of change is going to be negative. We have a negative slope on some of these. And so I went ahead and found the slopes. And if we plot these blue lines here, you can see that, yep, between 0 and 1, we have a positive rate of change. From 1 to 2, we have a positive rate of change. But then all of a sudden, from 2 to 3, we have a negative rate of change. And so when we talk about our rate of change being negative, if we look at what's happening in the real world, the distance is increasing, and then all of a sudden the distance is decreasing from where it started. So somewhere in there where we have that negative rate of change, that indicates that I'm going the opposite direction. So a little nugget of information to hang on there as we kind of talk about speed and velocity and rate of change. I know we've discussed velocity in the previous unit, and yeah, when you have negative velocity, it means you're going the opposite direction. So we've just movements of the object, we've estimated the derivative using the slopes, and we've considered this second set of data. And so I hope that this little introduction to this concept of derivatives is helpful to you. Keep in mind that there's going to come a time when we're going to find a faster way to evaluate these derivatives. But for right now, you need to be practicing those algebraic skills, and you need to be using that definition and applying it that way. It will show up on your AP exam in some way, shape, or form, so you'll be responsible to be familiar with that. But, you know, don't let the algebra keep you down. The more you practice it, the better you're going to get. I've seen it happen, and I know you can do it. I'm here for you, and my encouragement, as always, is to keep on going, because you've got this.